Welcome back. We're going to continue our review today. And here we are. We're going to do a reaction review. Sometimes when you're learning organic chemistry, it's helpful to see how the teacher designs questions. So we're supposed to know how to do a lot of things with alcohols. Let's start with one we already just did. How would I make that alcohol into this ketone? We'll not put answers here. I will leave the blanks here. I'm supposed to know how to do that. And we also looked at making alcohols into alkyl halides with a flipped stereocenter. This time I'll have a flipped bromide there. And we're all supposed to know how to make alcohols into ethers. Stereocenter the same this time. Let's put an ethyl group on there. I should take my own advice about the wedges and just use a fat triangle, shouldn't I? And what else do we know about what to do with alcohols? We're supposed to know how to make them into alkenes. And sometimes we're asked acid-base questions. If I wanted to make that alcohol into an alkoxide, yeah, a little messy here. And if it's a pKa question, I could give you some information. pKeq equals, what's 18 minus 40? That's negative 26. 22. Sorry. Okay. And we're all supposed to make alcohols into why not? Alkyl chloride. Make it a fairly comprehensive review with a flipped stereocenter. Or and we should always know what TS stands for. Separate question here, draw a TSO minus. And one more reaction of alcohols. Take it another step here. That is an azido group on there. So we got that, and we're going to do our answer on the second version right here. So we're going to brush up Should have our table of contents handy. And I have it over here. To put a BR reliably where you used to have an OH, some of you are thinking HBr. Let me tell you why HBr for making this product is not optimal. HBr will first protonate the O and make an oxonium. Secondary carbon with an oxonium has a couple options with almost equal energy requirements. It can do an SN1 reaction by going by a carbocation, or it can have a backside attack, which is the desired result, and give this result only. But a carbocation would give a racemization of stereocenters. You want to look at that. So a more reliable method is one where carbocations will not be generated. That is P, hello. Yeah, that's just like the old classroom computer there. PBr3. What section can you find PBr3 in? 10.4b. Please review that. Okay, let's stick with the halogen one since section 10.4 covers that. The one with the SOCl2 and pyridine, which we reviewed earlier today. And I'll tell you right now, you can use this short form for pyridine. It's acceptable and very common. I'm usually not a big fan of short forms. That would be 10.4C. And then the reaction where we made a ketone, we had lots of options. I'll put them all here. You can use the expensive one. Yeah. Ah, this stylus I'm using times out. And let's see, where are we at? We could use the PCC. That's not a very nice P. And PCC is found in, this is all in section 10.6. Or you can use the chromic acids that we looked at. CrO3, comma, H2SO4 in water. And I'm not going to write it here, but you could have replaced CrO3 with potassium dichromate, K2Cr2O7. Secondary alcohols, very flexible for oxidation. That's an oxidation when you create a new bond to oxygen that used to be a bond to hydrogen. Electrons got further away from carbon. That's oxidation. Okay, going to the top. Making an ether requires you first to make this into a nucleophile, an O- nucleophile. Oh, fancy that. We have an O- nucleophile right here. So why don't we do this first and then use that as the first step up here. That's an O- right there. pKeq negative 22 means you had to create an acid with a pKa of 40. How did I know that? pKeq, you want to review that in chapter 4. The alcohol is the reacting acid. I'm going to use the 18 here. Could have used 17. Reactant acids, pKa minus the product's acid pKa equals -22. So I'm not looking for HA in this box. I'm looking for its conjugate, you guessed it, conjugate base. So I need the conjugate base of an acid with a pKa of 40. Please, that pKa table never leaves your brain. The pKa table. The only acid with a pKa of 40 we ever learned was an amine. So I need the conjugate base of an amine. And you can use K. It turned off again? Nope. KNH2 if you want, or to make it organic, KNHCH3. Both would be a good example. Okay, acid base, chapter 4. And once you've made that, you now have a nucleophile. I'll use the other one that's simpler. You don't have to have a methyl on there. Good strong base. Takes the H off. And now you have an O minus. So I need some kind of an ethyl group. You see the ethyl group right here? An ethyl group that's going to be hit on the back side. So with a leaving group attached, so we can make the O bonded to the ethyl. How about ethyl bromide? ET attached to bromide. That's an SN2 reaction. Chapter 9, Introduction, Section 9.1. Oh. And acid base, Chapter 4. Okay, gotta go real slow with this pen. Learning as we go. All right, and this reaction here, you're stuck, you don't know what to do. You realize that this carbon here has 2 H's. And the same carbon here has only 1 in this product and this product here. And an H had to be removed. And that is called the beta position. And alpha is where the thing that leaves is, and it's an OH. Better make it a better leaving group. Some kind of strong acid could do that. Strong acids with alcohol and heat generate an elimination reaction. Elimination reactions of alcohols. It's called dehydration. Acid catalyzed dehydration of alcohols found in section 10.5. And our favorite acid for accomplishing that, sulfuric acid. And you're going to require a lot of heat. Alcohols don't like losing their OHs. Okay. And going downwards here, we're going to make what's called a tosylate ester. Tosylate ester. That's short form for para-toluene sulfonate. Tosylate. And we use TSCl. This box that we're filling in now doesn't have any restrictions on short forms. Sometimes there are. And much like the sulfur reaction to the left of it, we need a proton scavenger. Same one. And TSCl pyridine is found in section 10.4D. And this one here We got to do some thinking. Because right now it looks like some kind of a nucleophile replaced an OH, but the stereo center was maintained. Here it's R, here it's R. How do we do that? For example, if I react, I didn't draw my TSO minus. If I react, just an aside here, that carbon has a good leaving group. If I use chm242 and a polar aprotic solvent, and we're talking about analyzing reactions in chapter 9 here, and we'll have this box magically appear here that didn't exist on the original. I think you can still follow. You're not going to get the result that you desire here. You're going to get its complementary stereoisomer, aren't you? Backside attack is going to put the azide on a dash. So here your N3 will be here. This is what the N3 looks like over here. And we got an H up here. Okay, so that approach of first making a tosylate ester and then reacting it with azide is not going to give you full points here. But I do want to point out, if you did a backside attack on either this molecule here with azide or this molecule here with azide, you would get this result because the stereocenter got flipped and it's an SN2. So step 1, you can use PBr3 or SOCl2 and pyridine. And step 2, you can put KN3. And just for educational purpose, what's another polar aprotic solvent? We could use acetone. So when you go back to chapter 9, just review the 4 polar aprotic solvents. They're very good for SN2 reactions. We have dimethylformamide, DMF, acetone, dimethyl sulfoxide, and acetonitrile. And they all accomplish that. And finishing this segment, we're going to draw our TSO minus, because that tosylate, very common. Remember, the T is for toluene, which is just methylbenzene. There's methylbenzene. The S is for sulfonic something. There it is. And whatever's left over after, if it was TSCl, I'd write a Cl here. If it's TSO minus, I'll write an O minus here. To be able to draw that on demand. There's a nice little discussion of toluene sulfonic acid in chapter 4. I don't know if I can give you the section number. It really didn't hit the table of contents. But it explains this is really para-toluene sulfonic acid. Because of the positioning of the methyl group and the sulfonyl group. And it's not the sulfonic acid, it's the conjugate base. Resonating O's often end with ATE. So paratoluene sulfonate. So this brings to a close segment 3 of today's lecture, and I hope you found it useful in your review for Organic Chemistry 2. And I will try to close this out. Not getting any better at this. I think, why is it getting harder, not easier? Oh, here we are.